It's very, very rare in science that you make a big step forward in your measurement capability in the way that JWST has done for astronomy.
In the quiet hum of a control room, a transmission arrived from deep space. Light stretched thin by billions of years, yet unnervingly precise. It wasn't just a picture, it was a contradiction.
All these little dots are galaxies, some of which are bigger than our own.
Because it's too bright. And so we took better data, and in particular we also took spectroscopy.
A galaxy too bright, too early, too structured to exist. And as the data piled up, planets without stars, galaxies with scars of premature aging, chemical signatures that hint at breath, the message became clearer. This isn't the universe we thought we understood. It's something faster, stranger, and far more alive. The universe blinks first. For years, the Lambda Cold Dark Matter model, LCDM, served as the backbone of modern cosmology. It described a universe that expanded gradually, where galaxies assembled slowly, stars ignited in sequence, and time followed a predictable arc. But then came James Webb. With its infrared eyes peering deeper into time than ever before, it began returning images that didn't fit. Galaxies were forming too early, stars were dying too fast, and whole structures appeared before the laws of physics said they could. Some anomalies could be dismissed as errors in calibration, others as observational bias. But the pattern refused to fade. One galaxy, barely 300 million years old, showed signs of mature chemistry. Another glowed with a kind of light that shouldn't have made it through the early universe's opaque hydrogen fog. These weren't one-offs, they were warning signs. And the redshifted light wasn't the only thing bending expectations. Even closer to home, in the Orion Nebula, Webb spotted dozens of rogue gas giants, jumbos, drifting freely in space. But they weren't alone. They were moving in pairs. According to physics, this is nearly impossible. Planetary ejections are chaotic and violent. For two massive objects to be flung from a star system and remain gravitationally bound is like tossing two tennis balls into a hurricane and finding them orbiting each other on the other side. The universe wasn't just blinking, it was winking, daring us to catch up. The ghosts we weren't supposed to see. When James Webb's first ultra-deep images were unveiled, astronomers noticed something odd. Small, brilliant points of red scattered across the early universe. At first, they seemed insignificant, but as more observations poured in, the number grew. Hundreds of these compact anomalies were appearing. Too many, too bright, and too early. They weren't typical galaxies. They were far smaller, some only a few hundred light years across. Yet their brightness rivaled structures 10 times their size. They were nicknamed Little Red Dots. The name sounds harmless. The reality isn't. These objects shouldn't exist 600 million years after the Big Bang. Too young, too dense, too organized. Theories scrambled to keep up. Maybe they were baby galaxies glowing with intense star formation. Maybe they were early quasars, supermassive black holes devouring matter faster than light could escape. But they lacked the usual X-ray and radio signatures. They glowed, yes, but in silence. One idea gained traction. They could be cocooned quasars, black holes wrapped in thick blankets of gas and dust, hiding their violent cores. That would explain the lack of high-energy radiation. But it doesn't explain why there are so many of them, or why they vanish after the universe's first billion years. And then came something even stranger, UHZ-1. A newly identified galaxy with a black hole so massive it weighs as much as all the stars in the galaxy combined. In most galaxies, black holes make up a tiny fraction, about 0.1% of stellar mass. But this one is 1-to-1. It confirms a long-suspected theory: direct collapse. Some clouds of gas didn't bother forming stars at all. They folded inward, birthing black holes directly. No warning, no light, just gravitational surrender. If that's how the universe began, then perhaps what we see aren't galaxies forming too fast. Maybe they're just remnants of something that never formed at all. A signal that shouldn't exist. Among the oddities uncovered by Webb, one galaxy pierced through both time and theory. JADES GS 13-1. It shimmered like a relic from just a few 100 million years after the Big Bang, and at first glance, it resembled many of the ancient galaxies Webb was cataloging. But then scientists noticed something they never expected: Lyman alpha radiation. This specific wavelength of ultraviolet light is produced by hot, young stars, and it usually gets absorbed by the thick fog of neutral hydrogen that blanketed the early universe. During that period, known as the epoch of reionization, the cosmos was still opaque. Starlight couldn't travel far. It took hundreds of millions of years for the first stars and galaxies to ionize the fog and make space transparent. But JAIDA's GSZ 13-1 didn't get the memo. Its light cut through that hydrogen curtain with uncanny clarity. This shouldn't be possible. Unless, of course, reionization didn't unfold the way we thought. Maybe the process wasn't gradual or uniform. Maybe it was jagged and chaotic, localized explosions of clarity rather than a steady fade. A storm, not a sunrise. That alone would force a rewrite of the timeline, but it was only the beginning. Elsewhere in the Webb data, scientists identified Sears 2112, a barred spiral galaxy, virtually identical to the Milky Way, existing just 2 billion years after the Big Bang. Barred spirals are ancient structures. They're bars. The straight lines of stars across their centers take billions of years to stabilize. Yet here was a cosmic adult in a toddler's universe. Finding one that early is like walking into a preschool and meeting a child with a mortgage. Taken together, these discoveries suggest something radical. The early universe didn't just evolve quickly. It may have never followed the timeline we assigned it at all. Planets before time. While galaxies in the early universe were aging too fast, something equally unexpected was happening at the planetary scale. Worlds were forming before the stars had finished their lines. In 2025, astrophysicist Daniel Wan and his team ran simulations that turned the cosmic clock back farther than ever. They found that rocky planetesimals, those tiny, dense cores that become terrestrial planets, could have formed just 200 million years after the Big Bang. This wasn't supposed to happen until the universe had weathered multiple generations of star life and death, long enough to spread the heavy elements required for rocky crusts. But Wan's models showed it was possible even in the ashes of the first stars, which means planets, real ones, not just icy gas balls, could have been cradling liquid water almost from the start. And then came something no model predicted. In a planetary system just 120 light-years away, Webb focused on K218b, a Neptune-sized water world orbiting within its star's habitable zone. Inside its atmosphere, it detected dimethyl sulfide, or DMS, a molecule that, on Earth, is produced only by life, specifically by phytoplankton in the ocean. There is no known geological process that creates DMs. It's a tentative signal, yes, but if it holds up, it will mark the first direct evidence of biological activity beyond Earth. Meanwhile, in another system, Webb caught a more mechanical process at work. On WASP-39b, a hot gas giant, it detected sulfur dioxide, evidence of active photochemistry, where UV light breaks down atmospheric molecules and rebuilds them into new compounds. This is the same kind of molecular dance that may have seeded early Earth's atmosphere with precursors to life. Taken together, these observations suggest that the universe didn't just build planets early. It may have taught them to breathe. Dark energy refuses to sit still. For over 2 decades, dark energy was treated like a cosmic constant, an invisible force stretching space apart at a steady pace. It was built into the LCDM model as a quiet assumption, elegant and unchanging. But in 2025, the Dark Energy Spectroscopic Instrument, DESI, published a map so vast, it cracked that assumption open. DESI's three-dimensional universe chart revealed something strange. The large-scale clustering of galaxies didn't quite match expectations. The ripple patterns, fossils of sound waves from the early cosmos, appeared stretched in a way that implied dark energy had once been stronger than it is today. That defies the idea of a fixed cosmological constant. Instead, it suggests that dark energy may be a fluid force, changing with time, a concept known as quintessence. And then came a deeper shock. In a separate study, astronomer Alexis discovered a structure called the Big Ring, a massive arc of galaxies measuring 1.3 billion light-years across. It's so large that if you could see it from Earth, it would be 15 times the size of the moon in the night sky. According to the cosmological principle, such structures shouldn't exist. The universe is supposed to be smooth and uniform at grand scales. But the Big Ring, and its equally unsettling neighbor, the giant arc, suggests otherwise. The cosmos might not be shapeless after all. It may have texture, orientation, and design. The forces driving its expansion might not be acting equally in every direction. Dark energy, it turns out, may not be a steady push. It may be the pulse of something deeper and older, still unfolding. The spin we never felt. In 2025, astrophysicist Lior Shamir published a study that challenged one of the oldest and most sacred assumptions in cosmology, that the universe has no preferred direction. Using James Webb's deep sky data, he analyzed the spin of over 260 ancient spiral galaxies. What he found wasn't balance, it was bias. 2/3 of the galaxies rotated clockwise, while only a third spun the other way. In a truly isotropic universe, one with no special direction, this should never happen. The distribution should be roughly even. But it wasn't. The cosmos, it seemed, was twisting. This led some scientists to propose a bold idea. Perhaps the entire observable universe is rotating. And if that's true, the implications go far beyond symmetry. A spinning universe could bend space-time, alter the flow of light, and subtly skew the measurements we use to estimate things like dark energy. In fact, some theorists now believe this hidden rotation might explain why dark energy appears to fluctuate across time and space. It also reawakens a fringe theory with a disturbingly neat twist: black hole cosmology. The idea is simple but wild. What if our entire universe exists inside a rotating black hole? If you calculate the total mass of the observable universe and compress it, the result is an event horizon nearly identical in size to what we see. All known black holes spin. And maybe, so does the one we're inside. It's not just that the universe is expanding. It may be spiraling, with us caught in its quiet, endless whirl. We thought we'd mapped the stars, but it turns out we've only scratched at the shadows. If these mysteries move you, subscribe to keep exploring the edge of what we know, and share this with someone who still thinks space is silent.